So I was reviewing some of the old lectures on forms, and I realized I kind of glossed over something that can cause confusion if you start studying other books. So I want to quickly go over the normalization of forms. And I think this would be best inserted right after lesson 27 of what is a tensor. Right. So right after that lesson, maybe this little quick lesson would best fit. But the issue is that forms can be normalized a couple ways. And what lesson 27 offered up was the anti-symmetrization operator, which for P forms, or for rank 0P tensors, which I'll call KP. This all works for, of course, as usual, this all works for P vectors as well. But we'll just do it in terms of P tensors, this guy. And so the idea was you could take any tensor and run it through the anti-symmetrization operator, which was writing 1 over P factorial times multiplied by the sum over all permutations of the parity of the permutation multiplied by what we were calling the sigma transpose of the tensor T. And we went through this in lesson 27 about what this exactly meant. The point is I think I also demonstrated why this P factorial is in there. And the reason it's in there is we want this to equal T when T starts antisymmetric. So that's a very reasonable thing. So I want Kp of T to equal T whenever it's always true that P transpose of T equals, when the sigma transpose of T equals the parity of that transposition times T itself, right? When this is true for T, then this has to be true for the anti-symmetrized version of T. And we went through that proof in lesson 27. But that explains the origin of this factorial. So that's a really important place to start. And the other point I want to remind people of is that the sigma transpose of, say, a collection of say covectors that are tensor producted together, say there's a P of them, right? That is going to be equal by definition. So what I'm doing is I'm doing the sigma transpose of this guy here, right? That guy I might call, say, capital V or something. That's a tensor, right? So this here is a P, this here is a 0P rank tensor right here, and I'm just writing it all out. So it's P acting on this tensor. So I could call that P, the sigma transpose of the tensor V, right, is what I mean. And that's going to simply equal V of sigma inverse of 1, tensor product V of sigma inverse of 2, ... tensor product V of sigma inverse of P. And we went through this notation a little bit also in lesson 27 of what is a tensor. So that's the other interesting fact. But it's this last fact which I don't think I really emphasized a lot in the whole process of talking about forms in the What is a Tensor series. And let me go to this last one, which I want to begin to highlight. The last one looks like this. The last one is the wedge product of a series of 1 forms. That's what this means. This is the wedge product of P1 forms, so that this guy here is an element of the pth exterior power. That is, whoops, I've already screwed up what I'm trying to get across, right? That is, obviously, we know that this guy is going to be an antisymmetric tensor. And we want it to be related to the antisymmetrized part of the same vectors, the antisymmetry operator acting on the tensor product of V1, V2, and Vp. But if we just did this, if we just took the anti-symmetrization operator and acted on the tensor product of these guys, we would end up with a result that I'm not using. It's a convention, right? We can always throw a factor in front of this, right? We can define this wedge product to be the anti-symmetry operator acting on the tensor product times some arbitrary factor, and we can choose this arbitrary factor. So what I've been working with so far, the way I've been presenting it, I've been saying things like, okay, well, V1 wedge V2, I've wanted you to think in your mind as that V1 tensor product, V1 tensor product V2 minus V2 tensor product V1. So that's the wedge product that I've been using for between the two-form tensor product, right? Meaning the tensor product of two one-forms I've defined exactly this way. And other books do too, right? Meisner, Thorne, and Wheeler does it this way. Plenty of books will get you the wedge product this way. And if we did the wedge product of three, right? I'm not out there on a limb with this definition of how the wedge product should look. I should just anti-symmetrize these three guys in the tensor product space like we did, and that will be the definition of the wedge product of three one-forms, as written here, right? We want this to equal this. The problem is this guy here, if you operate using the definition of the anti-symmetrization operator, if you do that, this part here actually is, it's a process that goes over all these permutations. And you end up with this part giving you what you want here. That, in other words, the sum is this section. What I've written down is just this sum. For example, all the permutations, summing over all the permutations for this two form is 1, 2, and 2, 1. And that would be summing over all the permutations, including this parity factor. But this k also has this 1 over p factorial, right? So if I just define this to be the anti-symmetrization operator on the tensor product, I would get this multiplied by 1 over p factorial, right? So this whole thing would be in parentheses, and here I would have 1/2, and here I would have 1/6, right? But that's not the way we want this wedge product to be defined. We want the wedge product to be just the sum of the fully anti-symmetrized pieces, right? So we can't do the obvious wedge product definition, which is just to set it equal to the anti-symmetrized tensor product. But to make it all work, we have to choose a factor A that compensates for this leading factor that comes from this 1 over p factorial. So A is actually equal to p factorial. So this is the definition of the wedge product of a sequence of one forms. So I've rewritten it here. The wedge product of a sequence of one forms is p factorial times the anti-symmetrized tensor product of the same one forms. This is our definition, and it's not the only one. If you leave the p factorial off, right, if you leave the p factorial off, you just have to remember that V1 wedge V2 is 1 over 2 factorial V1 tensor product V2 minus V2 tensor product V1, right? So you're going to carry around this sort of normalization factor if you define it without the p factorial. But we do define it with the v factorial, so our answer should just be, that. and we want the p factorial there. Now that's our convention. That's the convention we use. There is the other convention is in use, but I wanted to make that very clear. If you wedge product a bunch of one forms, you actually have this p factorial here in the definition when you think about, because I really like thinking about it in this terms. I like going back to this sort of anti-symmetrized tensor product term. I really like thinking about it in this term too. Eventually you think about these things in an abstract way, and this becomes the elementary object. But every now and then I take that elementary object and I kind of pop back into this picture and write it as though it were an element of the 0p tensor product space, right? And I notice here, by the way, whether these are the names of one forms, right? So V1 is the name of some form, right? So V1 is probably actually going to be something like A alpha, E alpha, right? So the fact that there's a superscript there, that's part of the name of this thing. So whether I have superscripts or subscripts, obviously I named them with subscripts there. So this should have been a 1 and a 2 and a 1 and a 2 and a 1 and a 2. But when you're trying to write down a string of one forms, you just want to, instead of saying V, W, X, Y, and R, I just want to give them numbers. But that number is not, it's not a space-time index, or, I'm sorry, I guess I should say a vector space index, or a covector space index. It's just part of the name. Okay, so that's an important part of our convention. But there is an important implication to this that I want to talk to you about now, and it has to do with the inner product. But now we have this additional new issue. So once we've made our definition, now we have to ask the question, okay, what if we have one p form called V, and I wedge product with another p form called Q, right? So this is actually, we'll say that this is a p form, and this is a Q form. So we're actually going to wedge product a p form with a Q form. Well, our definition of how the wedge product works, right? This definition here now gives us a specific new rule for how this works. And that rule is p plus q factorial over p factorial q factorial times the anti-symmetrized V tensor product Q, right? Which, in another way of writing this, is P plus Q choose, well, I guess usually you say choose P, although you could choose Q as well. It'll be the same amount. Kp plus Q V tensor product Q. Now notice V tensor product Q, right? V is going to equal something that looks like V alpha, beta, gamma, E alpha, wedge, E beta, wedge. Well, let's just do wedge, E gamma, right? And there's going to be ultimately P of those, and Q is going to be Q delta sigma epsilon E delta wedge E sigma wedge E epsilon, right? And then there's going to be Q of those. So the tensor product is going to be this tensor product this. So it's going to be a wedge product, tensor product with another wedge product. So but remember, these wedge products, of course, they're just tensor products through this definition, right? Every wedge product is expressible as a tensor product. So ultimately, if you decompose this using this formula here, then you just have a large string of tensor products. So in here is a large collection of tensor products summed together, and it's summed together because this, remember, is a sum. The definition of the anti-symmetrization operator is already is already a sum, right, here through this thing. So that's a sum. So, but everything is linear, right? So it'll end up being the anti-symmetrization of a sum of simple tensor products. But notice this definition now has this factor in it up here. I don't think we discussed that in the What is a Tensor series, that this factor creeps in. If you want to see how that factor creeps in, I guess it's not too hard to show. We begin by looking at this kind of object. We have a simple P form, meaning it's just a collection of, it's just a wedge product of P1 forms, and a simple Q form, right? And our goal is to wedge this simple P form with this simple Q form. Now, if you followed the What is a Tensor lecture, you know that this is going to result in a P plus Q form. But what I probably didn't go through is that by definition, we want this wedge product to equal the obvious thing, which is the wedge product of the two, right? We just want to be able to say, oh, if this is simple and this is simple, and we take the wedge product, this is a P plus Q form, and it's just the wedge of the two together. We want that to be the case. So, all right, so how would we actually execute this kind of thing? Well, we might have started by saying, oh, well, V wedge Q, where this is Q and this is V right now, that's going to be the anti-symmetrized P plus Q form of V tensor product Q. Right? We take the tensor product of this thing, which is going to be, the tensor product of this is going to be a sum, because remember, this is the sum, this wedge product is the sum of a whole bunch of tensor products anti-symmetrized, and so is this. So I'm now thinking, well, if I'm going to wedge these two together, I want it to be the completely anti-symmetrized version of the tensor product of those two, right? Maybe that's what I want. I want it certainly nice and simple. Wouldn't it be nice and simple if that were the case? So let's calculate this and see if we end up with this answer, right? And if we don't end up with this answer, we might discover that there's a constant here that we want to throw in so that we do end up with this answer. So our goal is actually to define the wedge product of a P form with a Q form in such a way that this is the answer. And remember, we have the right to define it, right? Everything being linear, throwing in factors here and there really doesn't matter, doesn't amount to much. But it's our choice on how these symbols should operate. The key thing is that everything needs to be anti-symmetric all the time. These factors are there for our convenience. Even, by the way, the factor here, this factor, 1 over P, this was driven, we're defining the anti-symmetrization operator. And we just said, hey, we want it to be that when you take the anti-symmetrization operator and act on an already anti-symmetric tensor, we want you to get the tensor back. We don't want there to be any factor in front of it, right? But if there was a factor in front of it, it wouldn't crush any of our work. It wouldn't do total damage to our future work. We just have to kind of keep track of where that factor flows through all of our future work. And, whatever, right? If we choose that factor to be 1, it's just particularly convenient. And in order for that factor to actually be 1, we have to throw this 1 over P factorial here. So again, that's arbitrary. We could have done without this. And it just would have been the case that the anti-symmetrized version of an anti-symmetric tensor was not itself. It was some factor times itself. But so we had the choice to define it the way we wanted to define it. And likewise, we did the same thing back here, or down here. We said, well, we want the wedge product of two vectors to simply be the obviously anti-symmetrized pair. So that was our choice. Other people actually made the other choice. They said, yeah, the anti-symmetrized pair, but we want this factor of 1/2 because here's one object and here's 2 objects. So somehow we want that fact that one object's becoming 2 objects to be compensated for by a numerical factor out there. And maybe that'll help us later. And there are some reasons why this is actually a preferred normalization. There are some mathematicians who've written books about this who use this normalization because it's more convenient for some other purpose. But we chose, no, we don't want that normalization. But in order to get it, we have to add this factor in front. So we're so insistent on this that we add a factor up here so that what might obviously be the definition, right, just the anti-symmetrized tensor product becomes the wedge product. That would be the obvious definition, but we say, no, we want the P there also. Right? So we're doing the same thing here. We're now talking about the wedge product of a P form and a Q form, and we want the answer to look like this. This would normally be, without this any factor here, that would normally be the sort of obvious thing to do. But does it give us what we want as far as the result goes for a simple P form and a simple Q form? So we could plug and chug to see what answer this actually is. So let's do that. Okay, so what I'll do is, in order to highlight the fact that we're looking to decide what we want some arbitrary factor to be, I'm actually going to put it in there and call it A. So I replace the anti-symmetrization operator with its definition. So we're going to sum over all permutations called gamma. There's the parity of gamma. There's the gamma transpose operator. This is the V tensor product Q. So this part here is that part there. Oh, and then there's a factor of 1 over the P plus Q factorial, right? Because that's part of, that goes all the way back to this P factorial here, the one that I've been crossing out over and over again, right? That P factorial is now P plus Q factorial because we're dealing with KP plus Q, right? Okay. So, and then I keep this little A there. All right, so now I'm going to substitute for V and substitute for Q, right? And remember, V and Q are just these simple wedge products. So they're easy to put in there. All right, so the blue is now, this part of the blue is the substitution for V. This part of the blue is the substitution for Q. And the only part that's missing is there's a factorial in front as part of the definition of the anti-symmetrization operator on P and the anti-symmetrization operator on Q. So what that means is since V is just this strict wedge product, the definition now I have a P factorial here and a Q factorial here, which I'm going to bring out in front. Wait. Let me say that correctly. Let me say that one more time. The definition of this guy right here, right, based on our convention, is going to be P factorial times the sum over, well, it's going to be P factorial times the P transpose of V1 tensor product VP, right, which is P factorial times 1 over P factorial times the sum over all, I guess I'm using sigma, parity sigma, sigma transpose, V1 tensor product, to VP. Right, so these cancel, right? And that's why you don't see any additional P or Q factorials here and here, because this is our definition of the wedge product of a bunch of one forms. So P1 forms, wedge product together, this is the definition. And our definition includes a P factorial here. Our convention includes a P factorial here. So that cancels with this one. So all I need for that simple P form, this simple P form, is just the summation. And that's what I've put in here. Okay. So the next step. All right, so the next step, all I'm doing now is I'm taking this summation and this summation. Everything's linear over the tensor product, so I can pull those two sums out here. The parities, they're just constants, and again, the linearity allows us to pull that right out. So now I've got the two sums and the two parities all together, and then I just have the tensor product of this p transposed set of v's and the p transposed set of pi. So I've got that going right there. Then the next step, we'll use the definition of the transpose, the p or the p transpose or the sigma transpose operator on this, and the sigma transposed or the pi transpose operator on that, which you remember is applying the inverse of the actual permutation on the indices of the objects that are of the tensor product. So I'm going to substitute a way for these two guys through the definition of the transpose operator. And I did that exchange in green. So here you see the this transposition, or this sigma transpose is applied here, right? So remember, the inverse is what ends up, we're shuffling these around using the inverse of the transpose operator. Because remember, the transpose operator technically is designed to shuffle around the arguments of this tensor. So you would give this tensor a bunch of vector arguments, because remember, these are one forms, even though there's a superscript here. Remember, the superscript is the name of the thing, not the thing. So you give each of these one forms a vector to eat. Normally, this would shuffle around the arguments of those vectors, but you can take the inverse and shuffle around the components of the underlying tensor, which is what we've done here. So we have all these inverses. And here, what's an important thing to know is that I think this should be relatively obvious, but the parity of a permutation is equal to the parity of its inverse. So I can actually swap these guys out too. And I swap them out with their inverse, and that's fine. And notice that I'm summing over all possible permutations. So by summing over all possible permutations, that includes every permutation and its inverse. So if I sum over all the inverse permutations, I'm still ending up summing over all the permutations. So I can swap these out for the inverse permutations, and this whole thing will now be defined in terms of inverse permutations. Now, it also doesn't take too much thought to realize I'm going to end up redundant. I'm going to end up counting the same permuted object q factorial times, and p factorial times, or the product of p factorial times the product of q factorial times. This sum is going to be highly redundant. And that redundancy is totally quantifiable as a p factorial redundancy for the p vector part and a q factorial redundancy for the q vector part. And so all of this, the sums can be eliminated by just including a multiple of p factorial and q factorial, like this, by just going p factorial, q factorial. I can now erase the sums, right, because of the high level of redundancy there. And so now, now we understand too that there's an additional redundancy that takes care of these sigmas, because for every pair of permutations sigma and pi, or sigma inverse and pi, there's a sigma gamma that you can imagine is the inverse of that pairing, which will always sort of compensate for these sigmas. And so because I'm summing over every permutation here, I only need to maintain one permutation symbol, and these two can be eliminated, right? And so now we end up with simply this object, but I can, in addition, these sigmas are now gone, right? I just can choose one single permutation. I want to sum over all the permutations gamma. So I don't even need these sigma inverses anymore. I can actually erase those. I can erase those and just return it to 1, 2, 1, 1, P, V1Q, because wrapped up in every permutation gamma are all the product sigma inverse and pi inverse permutations. There's another gamma that's going to get that permutation, that particular pi and sigma permutation, to whatever gamma I would have chosen had these been absent, right? Because I'm summing over every permutation. So there's a high level of redundancy in all of this. But these guys are compensated for by this p and q factorial. And what's left is now the gamma permutation of all of this stuff. And that's fine, because the gamma permutation of all this stuff is, by definition, right? By definition, this part here, this 1 over p plus q factorial times this, right? That's going to end up being equal to this, right? The 1 over p plus q jumps in with that, and that is the definition of the anti-symmetrization operator for a p plus q form, right? That's what this now is. Here's the p plus q form. So this guy is this, and now we have the p factorial, q factorial redundancy, and then there's this a still floating around. Okay, so that's pretty close, but we want this thing, remember, our goal is that this answer here, right, needs to equal this answer here. And this answer here is purely given by this part without that factor. So what we'll do is we'll pull that factor out. We will, let's see if I can do this. We'll pull that factor back out. I don't want to do it in red, I want to do it in black. We'll pull that factor back out, so we'll get p factorial, q factorial, p plus q factorial times a. And then this sum that's left behind, we already know that that is v1 wedge, v2 dot dot, vp wedge, w1 wedge, w2 dot dot dot, wq. And now we know that this guy here needs to equal 1. So A has to be p plus q factorial over p factorial q factorial, which is the definition that I offered in the beginning. Phew. Okay, so this weird normalization factor has to appear because of the way we want a p form multiplied by a q form to turn out. Okay, and I just sort of proved it by using direct substitution. And the fact of our original choice of definition, of this p factorial right here, that flowed into our definition of this choice here, right? That choice here, when we did the proof, or we did that's hardly a proof, right? The demonstration, when we made the substitution for v and q for the simple p form and the simple q form, because we want a simple p form wedged with a simple q form to just be the wedge of the two simple forms. Whereas a reminder, a simple p form is just a straight wedge product of a bunch of one forms, and a simple q form is a straight wedge product of a bunch of one forms, of q one forms and of p one forms. So we want the wedge product of p one forms. When we wedge that into the wedge product of q one forms, we want just a simple, straightforward wedge product of p plus q one forms, which is what this is, p plus q one forms. And in order for that to be the case, we actually have to define that wedge product between a p form and a q form to have this additional factor in there. Okay? And that all flows from these factors that we chose in the beginning. The one that was sort of forced upon us by really reasonable logic, that the anti-symmetrized part of an anti-symmetric tensor should be itself, right? The anti-symmetry operator acting on an anti-symmetric tensor should be the tensor itself. That's sort of the reasonable statement. And from that, we end up with this 1 factorial forced upon us. and then we choose that we like our wedge products to not have any factors, so we put the factor in the definition of the wedge product, and that ends up forcing us to have a factor in the definition of the wedge product of a P plus Q form. Okay, so that was what I wanted to get across, just a little bit about the normalization, but I think that's the only really tricky thing. But this does have an implication for the definition of inner products, and I might as well include that as well. All right, so now let's look at this guy right here. We have a simple P form, these omega 1, omega P, where each individual P form is named with a superscript, right? And it's being fed P vectors, right? P forms are still 0P tensors, right? So 0P tensors eat P vectors. And so given that, we replace this 0P tensor with its definition. And our definition includes our normalization factor, P factorial, of the anti-symmetry operator acting on the tensor product of the same one forms. That's the definition of this wedge product of P1 forms. And our normalization, our preferred normalization, is this P factorial, so that we carry that along. So we make that substitution in here, and we get, there's our normalization P factorial. This object is defined as the anti-symmetrization operator of this simple P form, and that includes its own 1 over P factorial, right? That's the one basically this is designed to compensate for, which it nicely will. And then you're left with the straight up sum of all the permutations of the tensor multiplied by the parity. And then that straight up sum is a tensor that will be gobbling up these P vectors. And so now we do sort of the same thing we did before. We actually execute the P transpose operator, and that gives us these inverse operators on the tensor. So instead of reshuffling the P transpose operator is sort of defined by the reshuffling of the arguments, but instead of reshuffling the arguments, we're just going to shuffle the actual tensor component itself, right, with the inverse. So we've discussed that in the lesson 27. And then we use the usual fact that the parity of sigma and the parity of sigma inverse are the same. And the fact that that combined with the fact that we're summing over every sigma means that we can actually just get rid of these inverses altogether, right? It's just that convenient and that easy to do. And then we ask ourselves, okay, well, this we know. We know how a tensor operates on, a straightforward tensor product operates on a P tuple of vectors, right? So let's just make that substitution. And that answer is right here. This is important to understand. The mapping of the tensor product on the P tuple is the product of each individual one form's mapping on the associated vector, and that's what this guy here is. But we're summing over every sigma, right? And if you understand how this works, we can actually convert this into sort of an Einstein sum, not even sort of, a literal Einstein sum. And in this form, we're now summing over all i's in the parity operator being summed over all of these i's in these objects, these products, or these dual space mappings, which are numbers, right? That's a number, that's a number, that's a number. This is a number, it's plus or minus 1. So this whole thing is just a number. But if you look closely and you go back to, I'm pretty sure we did a lecture on this as well, this is simply the determinant, right? It's the determinant of a matrix, omega 1 V1, or actually in this case it would be, omega 1 V1 omega P VP, and then down here it'll be, that's going to equal this determinant, right? The determinant of omega 1, v1, this matrix you can make if you made a matrix of these guys that look like this, you get this determinant. That's what this defines. This defines the determinant of the matrix that has these components, these entries in the matrix. This would be the I1, the omega, or the ith row, 1th column, the I2th row, the 2nd column, the ith row, pth column. And notice these are fixed. 1, 2, all the way through p is fixed for the vectors, but it's the covectors that are summed over. And it turns out that's exactly equal to the determinant of the matrix. So the point being that a p form operating on p vectors, it's very nice and simple. It's simply the determinant of these individual dual space mappings. And this is the dual space mapping this is the operation of this tensor. So the operation of this tensor on p vectors is the determinant of these individual mappings. Now, the last thing I want to emphasize here that our convention kind of rolls into, I guess what happened back here, our convention showed up here, right here, right? So that's where our convention showed up again. But the convention helped us because it ends up with this nice determinant answer. In the case of inner products, it doesn't work out so nicely. So let's remember the underlying vector space has, let's say it has an inner product established on it. And we call that inner product V. Then the tensor product space inherits an inner product, which we'll call P. So if it's a 0P inner product space, I'll just put the P here. It inherits an inner product from the underlying vector product space. If you don't remember how, it's pretty obvious. The inner product of two 0P tensors is going to end up being the product of the decomposition of those tensors using this inner product, and we'll review that in a moment. But this guy, remember, is an element of this tensor product space. So you might think that, well, the inner product on this space, this exterior power space, well, that's going to be the same inner product as this one. Why not? This is actually a subset of that. And you could do that, right? You could do that. That is sort of the obvious thing to do. But we actually changed the definition a little bit in order to make it look good again. And that's why I'm going to say this inner product is actually going to be slightly different. And I want to exercise all that for you right now. So let's look now at the inner products. The underlying vector space V is going to be given an inner product. I'll call that inner product V. The tensor product space, the 0P rank tensor product space built off of V, it's going to have an inherited inner product, which we will call with a little p there for, I guess, 0p. Now, the exterior power, the pth exterior power, which is a subset of the 0p tensor product space, it's also going to inherit an inner product, which we'll call p hat. Now, the key is, though, is the p hat is pretty obvious. These guys are all members of this tensor product space. So that being the case, p hat should just equal p, right? Right? Because why not? I mean, if the underlying vector space has been given an inner product that is automatically inherited by the tensor product space, then clearly any subset of the tensor product space should inherit that inner product. And in fact, it does. It does. However, remember, inner products are something we can define, and they're linear. So it never really hurts us to include factors, right, in front of them if we want to change them for whatever reason for our preferences of normalization, right? So it turns out in the case of the inherited inner product on the tensor product space, we don't have any factor, or the factor is equal to 1. But that's not the case for the exterior power. There's something nice that we want to have happen for the inner product of the exterior power that we will include a factor. Notice here, when we did the obvious thing of feeding a p-form p vectors, it all worked out really nicely. We ended up with this beautiful determinant. So we could have, unfortunately, that's not going to happen in this case, and we're going to need a little factor. So let's see how this works out. So I'm going to try to study the inner product of two p-forms, right? They're both going to be simple, because remember, once we can do it for simple ones, it's by linearity. Anything that's not simple will be just some sum of this exercise that we're going to do on the simple forms. And they're both p forms, so they were talking about an inner product on the tensor product space P, which is a vector space, and this vector space has an inner product. And we're going to assume this is true for right now. We're going to assume that we're just going to use the inherited inner product, the inner product that was inherited from V into the total tensor product space. We're going to assume that our exterior power inherits the same thing. And if you've forgotten how that works, by the way, if you've forgotten how this tensor product space inherits an inner product from the underlying vector space, I'll show that I'll review that in a split second here. But the first thing we do is we just make the substitutions right here for these two objects, which we've been working on in this lecture a couple times already, right? This substitution here is very simple, right? This simple, the inner product of P1 forms, where remember these are the names, these superscripts are the names of the one forms, and V is a one form, although this is still true for vectors as well, right? One vectors. But nevertheless, it equals, by our definition, by our definition, our previously chosen convention, it equals P factorial times the anti-symmetrization operator of the tensor product of those P1 forms, right? And here, this guy here is 1 over P factorial times the parity operator times the sigma transpose operator. So I've done all this. The sigma transpose operator I've already interjected right here by these sigmas, but I've used the fact that we're summing over every one, so I don't need to use sigma inverse, right? Because we're doing all of these sums. We're summing over every permutation, and I know that the sigma, the parity of sigma and the parity of sigma inverse are the same. So I've taken a few steps because we did those steps before. So this guy right here is what that is. And these factorials go away because our convention eliminates the factorial on the anti-symmetrization operator. And now I just added it for W, sort of the exact same thing for W. And we're talking now about the inner product, right? The inner product of this in P hat, but I've decided that P hat equals P for our test run here because I think, oh, that should work out just great. And so I will get rid of the hat for now. Okay, so let's now exploit linearity, and linearity lets us pull out the sum and the parity number. Parity is just a constant. It's sum. Since everything's linear, we can pull out that sum, and we're left behind with something relatively simple and obvious, which, let's see if I did this right. Right, this guy here ends up being the tensor, the P tensor here, and this is a P tensor here. So now I have two elements as written that are in T0P, right? That's an element of T0P, and so is that. That's an element of T0P. So these are both elements of T0P. And now I'm looking for the inner product of two elements using the inner product of T0P. Well, and this is where the review comes in, right? That's just going to be V sigma 1 inner product W pi 1 multiplied by V sigma 2 W pi 2 ... looks bad. Pi 2 ... V sigma P W pi P. And that's obviously like the only way to do this linearly, by the way. So now, and these guys are in V, which we know, right? We know V, because remember, this whole thing was premised on we understand the inner product in V, and that inner product gets inherited by T. Inherited means, as a reminder, inherited just means there's a canonical choice of inner product on the tensor product space if you know an inner product on V. And likewise, there's a canonical choice on lambda P. So we're going to use all these canonical choices. And so far, if we use all those canonical choices, we end up substituting this this tensor product in this inner product of these two members of T0P with this product of inner products. So what does this thing look like? Well, let's see, hold on. What does this look like, right? I'm now substituting that product in there. Well, it turns out, just like back here, when we looked at and we studied this thing, we realized, hey, wait a minute, that equals the determinant, right? But notice this is different. There's only one parity operator being summed over, and over one string of indices. These guys are fixed, 1, 2, all the way to P. So in our case here, we actually have two parity operators, and the sum is over all of sigma and all of pi and all of sigma. And so each of these have two indices, and they're all being summed over. So it turns out that if you go back to our determinant lecture, this is going to actually equal, and I'll write it in red, it's going to actually equal p factorial times the determinant of this obvious matrix, right? And that's the problem, right? The problem is that the inner product of two simple p forms is not just this nice determinant of these inner products that go all the way back to the original vector space. It's p factorial times that, right? So that's the price we pay for doing the obvious thing and saying that the inner product defined on the exterior power space equals the inner product defined on the underlying tensor product space. If you do that, you end up with this p factorial factor out there that's generally, we could live with it. The problem with living with it is the orthogonality of basis vectors, right? If I have E1 inner product, wedge product E2 ... wedge product EP, E1 wedge product E2 ... EP, right? This is a basis vector of the exterior power space. And this is the same basis vector. So the inner product of those two basis vectors, if we use the inherited inner product, that inner product is going to equal p factorial, because this determinant is going to be 1, right? The value of the determinant is going to end up being 1. And you can see, as that's going to be E1 inner product E1, which is equal to 1, or, it could in principle be minus 1. And this one is going to be E1 EP, which is going to be 0, right? So the only thing is going to be this diagonal row is going to end up being the value of the determinant, because it's assuming that E1, yes, we have to assume that the underlying basis vectors are orthogonal themselves, right? So that E alpha E beta in V equals delta alpha beta. If that's true, if the underlying vector space is basis vectors are orthogonal, then the basis vectors of those guys in the pth exterior power, they won't be orthogonal. They'll be p factorial. Their inner product with each other will be p factorial. So we don't like that. We want this inner product to actually be, in this case, we want the inner product to be 1, right? For this particular set, or for any set of the same basis vectors, right? We want it to be, well, look, the bottom line is we want all the basis vectors of this vector product space to be orthonormal, and that's the normal part. And right now we're not normal, we're at p factorial. And that's the price we get if we insist on this, right? If we insist on this, that this should be smaller. If we insist that the inherited inner product, if we insist on using the totally inherited inner product on the exterior power space, we lose orthonormality is essentially the problem. So what do? Well, we do the obvious thing. We say the inner product in the pth exterior power is 1 over p factorial times the inner product that's inherited by the tensor product space. This is our new definition. So I'll give it little 3 lines. This is the new definition. That is how we define the inner product on the exterior power. So if you notice, if we did that, we would have gone all the way to where we would have now had. We've now called this instead of just p here, we would have thrown down a 1 over p factorial there, and that would have flowed all the way to here, 1 over p factorial. That would have canceled, and we would have retrieved orthonormality. So that's the little quirk. Now notice that in this case, though, I can't blame the quirk on our convention, right? Because if we went all the way back here, and I'll go to green now, right? If we go back to this place here, this is where our convention was. Our convention here has a 1 over p factorial canceled by a p factorial, right? And so that's our convention cancels those two out. But if we didn't use our convention, we would have left a 1 over p factorial there and a 1 over p factorial there, right? So, and then, so what would have happened in that case? Well, in that case, remember now, we would have gone through this whole exercise, and we would have ended up with, we would have ended up here, and this would have had remember we did the calculation, p factorial, but it would have had in the denominator 1 over p factorial squared, right? Because this 1 over p factorial and that 1 over p factorial, they both would have come out front. So you would have had a 1 over p factorial squared out there. And that cancels the p factorial, but it leaves a 1 over p factorial in the denominator. So when this cleans up, it would have ended up with 1 over p factorial times the determinant, and the orthonormality would have been blown in the other direction, right? The orthonormality would have been 1 over p factorial instead of p factorial. So you still would have had to screw around here, but in this case, you would have had to put p factorial there. So our normalization doesn't really screw up the inner product problem. The inner product problem exists with either normalization. Okay, anyway, so there's a long lecture about normalization conventions in this mess. It's not that insightful, but it is important when you work with this and from other books is to get a grip on what that is. Okay, so thank you for letting me squeeze in this supplementary lecture, and I'll see you next time.